Hello, everybody. We have a midterm on Thursday, and I want to say a few things about that, or just a little bit about that. Let's see. So there is no homework as of now. There will be a homework after midterm 4. Midterm 4 is on Thursday. It'll cover everything. Cover which are the homeworks? Let's see. Homework. Basically 8, 9A and B, right? And what? A and 9B. And the only small change that might happen is my expect. I haven't decided on this. Expect more conceptual questions. I used to give 4 conceptual questions and about 7 or 8 long questions. What I'm planning to do is trying to do more conceptual questions, and that is mainly to experiment if I can do more conceptual questions in the final exam. So I want to check how you guys handle conceptual questions so that I don't end up giving too many conceptual questions in the final exam and it shouldn't hurt you. So this is going to be a small experiment on that basis. So how could be the distribution? Maybe more than 6 conceptual questions in here. Again, I'm debating on that, how many exactly to put in, but that will be the only change. Otherwise, everything as far as the how we complete and how we submit the exams, everything remains the same. Just the question style might change. Any questions on that? Okay, if not, let's proceed. After midterm 4, there will be a one final homework. So that's homework 10. That will be due on December 3, which is Thursday, which is the last day of class. Again, this is an online course, so I don't have to say that this will switch over to online. So, and this will be uploaded after midterm 4. Okay. Today's lecture will not be covered in the midterm. That's typically how I've been doing this semester. We cover everything that's necessary one lecture before. Right? So today we want to do simple harmonic motion. And this is related to what we covered some time ago on Hooke's law. And this is a very particular motion, a slightly more complicated motion than what we have been talking about until now, in the sense that the position itself does not change linearly with time. So that is a non-monotonic I shouldn't say non-monotonic, it doesn't keep increasing with time. For some moment, it increases, then decreases, increases, and decreases. And more correctly, it is an oscillatory motion. Here it's called harmonic motion. So let's remind ourselves of a spring. So this is a review a little bit. So we define a spring as, let's say there is a horizontal floor. So this is a floor, and you have a spring attached to the one wall, and there is a mass sitting on the floor or on a table. And that point where it is, the spring is neither stretched nor compressed, this will be called the position x equal to 0. That's the equilibrium position. We say that this is frictionless and horizontal. Frictionless and it is horizontal. There are forces acting on this. There is mg acting downwards, and the normal force is acting upward. But our interest is primarily in the motion in this direction. So mg and n will also always cancel each other, so that won't be of much significant importance here. Now let's, what we did earlier was how do we introduce the idea of a spring force. You stretch this mass out. So you stretch the spring. So this is a stretched spring, and the mass comes somewhere here. It's the same mass, m, let's say. And now, since you have stretched it, the spring tries to pull it towards the equilibrium point, and that's a force F. And that force is, this was x equal to 0. Let's say this is the amount of stretch you have made. So that's the position x now. So x is measured away from 0. How much the mass has displaced from x equal to 0. Here x is greater than 0. So the force will be towards the origin all the time. So in this case, it is minus kx. And that introduces the concept of spring constant k. So k is equal to a spring constant. If it's a stiff spring, it can be a very large number. If it's a soft spring, it's a smaller number. And we talked about this before. The main idea here is that the force is towards the origin. If you make a positive displacement, force is in the negative direction, opposite to the displacement. There is one more situation possible in the extreme scenario, and that's still visible on the screen. So that's x equal to 0. This time, compress the spring, keep the mass somewhere here. So that way, x is now negative, and the spring can be shown as a compression. So this is a stretched spring, and this is a compressed spring. Again, the force is equal to minus of kx, but it is in the positive direction because x is negative, right? Since x is less than 0, x is negative. Negative of a negative number is in the positive direction. So the force is in the opposite direction of the relative to, if you were to compare it with the time when it was actually stretched to, when it was stretched versus compression. So that's the idea of a spring force, which we did before, and then we talked about how much energy is stored in the spring and so on. Here, we want to really actually talk about this motion instead of keeping this static. If you were to pull this, stretch this to the right as we did here, and then release this, we expect that it will go back to equilibrium. That's why it's called the equilibrium position. But instead of reaching and coming to a stop at x equal to 0, it will overshoot this point, and if it is completely frictionless, go all the way to the same point where the maximum x goes. So it'll come here, get compressed, and then again push that way, and this might oscillate. So this to and fro behavior is what will be called oscillation, right? Simple harmonic motion. So let's let me define that. So expectation is, we will make this more precise. Intuitively, the expectation is that if you were to pull this mass or stretch this mass out and release it, there will be a to and fro motion. And technically, this motion is called an oscillation, or more precisely, a simple harmonic motion. So this is called an oscillation, or simple harmonic motion. Under these assumptions that we have no friction and everything is horizontal. And even though we are going to build this analysis in the context of a spring being pulled or compressed, we will very quickly make a leap and be able to analyze any such motion which has a small disturbance about a point. So whenever you can shift a system away from equilibrium, and it can come back, and the tendency for it is to come back to equilibrium, that it will always do simple harmonic motion. So that will be a conceptual leap, but let's first analyze this motion. Okay. Okay, so we pointed out that for a simple harmonic motion, or for oscillations with respect to a spring, we have force given by F is equal to minus Kx. So that's going to be our first point, where K is a spring constant. If that's the only force acting on the system, and in this case, as far as horizontal forces go, that's the only force acting. So mass times acceleration in the x direction, since we're talking about the motion in the x direction, is equal to minus k times x. That's just rewriting the same expression using Newton's law. This is the actual force acting on the spring, but Newton tells us that mass times acceleration has to be equal to the sum of forces. There's only one force acting in the horizontal direction, so it's minus kx. Again, remember, this is your mass m, that's your mg, that's your normal force. And if it was stretched to the right, so there's a spring force acting, that's minus kx. There's three forces acting, but in the horizontal direction, there's only one force acting, so that's mass times acceleration has to be equal to minus kx. Let's make a definition right away. Since there is k and m coming, there seems to be two parameters, but I can divide by the mass so that I get rid of one of the parameters. So ax is equal to k over m, which I will define. So this is k over m, which I'm going to define k over m to be equal to some omega square. Right, so omega is in rotational motion. We found angular velocity was represented by the letter omega. It will play the same role, and even before that, we had angular frequency for 2 pi over time period when we were talking about centripetal acceleration. And again, that's exactly the same omega that is showing up, but at this point it is not very clear what exactly that is. But whatever that is, let's put that in here. We'll come to the interpretation part in a moment. So our motion is described by acceleration is equal to minus omega square x. Let's think about this a little more. Acceleration is change in velocity over change in time. That's equal to minus omega square times x. Right, so here we have position, change in position is velocity, change in velocity over time is acceleration. That's related to the position itself. So let's do this better. Let's make this more precise. So change in velocity itself is change in position over time. So that seems to be very complicated, right? Over change in time. So change in velocity is related to negative position, but velocity itself is change in position over time. It seems to be a second order change, right? So that's equal to minus omega square x. That's a lot of writing here. So let's have a notation now. So this is just simply a notation, which means exactly this. So we are going to say change in something will be denoted by delta square and delta t square. This is just a symbol. So this is just a symbol which should be treated as one piece. Right? So this is one. So this is a whole thing is a symbol. You won't be using it too much, but I don't want you guys to get confused. This is change. So this whole big understanding, like change in something divided by change, which in itself is a change, will be denoted by, so second order change in position is equal to the position itself. Right? That's our our defining quantity. The change, like second order change in x is related to x itself. So let me write that down. Second order or second change in position with time, with respect to time. Time is proportional to position. And we would like to investigate what kind of motion gives you this, where the second change or the acceleration is related to position actually. So if you're farther, you have more acceleration. If you're closer, you have no acceleration. So again, notice what's happening. So there is a mass which is at x equal to 0. That's in equilibrium. If you pull it to this point, that has been stretched. So it tries to come here. And if it is at this point, it has been compressed, it tries to go away. So acceleration is dependent on position. So what is the acceleration at this point? It's 0. If acceleration is 0, force is 0. At this point, the force is maximum. So if it is on the extreme right, so force is maximum, and it is negative of that, so that's in this direction. So acceleration is also towards the center, and the acceleration when it is in here, that's in the towards the right. And right at this point, acceleration is equal to 0. When you reach x equal to 0, acceleration is 0. That doesn't mean that velocity is 0. When it is coming here, it might overshoot that. It is exactly like throwing a ball up in the air. Velocity equal to 0 doesn't mean acceleration is 0. Similarly, acceleration is equal to 0 doesn't mean that the velocity should be 0. That's not necessarily one. But again, we want to actually see what this motion is. So we will have an analogy now. So how can we get a feel for this motion? This will be actually a to and fro motion. That will be an oscillatory motion. But we want to make this very precise. What exactly is the motion? So we make an analogy here. So let's think of a circular. So we are going to make a connection between circular motion and simple harmonic motion. And circular motion is a familiar idea. We already know it. So that will be the point we will use. So let's have circular motion. So that's a circle. And let's say that's the center of the circle. And let's have the horizontal axis specified. And that's, let's say, the object that is moving in a circle. It starts at time t equal to 0. It starts from here and then it moves uniformly. By uniform, I mean it's not angular. In the angular sense, it's not accelerating. It is uniformly going around the circle. So so there's a fixed time period. It slowly goes here, comes back again, repeats, keeps repeating, and it's not doing acceleration. Right? It is slowly uniformly moving. That means to say, if it is uniformly moving, so this angle theta here is increasing. So that arrow means that it is increasing in that direction, and that angle theta is uniformly increasing. That means there is an angular velocity times time. Change in angle is over change in time is a constant. That means position goes linearly with time. In linear motion, this would be x is equal to vt. That means there is no acceleration. Acceleration requires a second order or second power in t. Half at square would be the acceleration. So it's not acceleration accelerating in the rotational sense. So this is omega t. So that angle theta is nothing but omega t. And let the radius of this, usually we call it radius r. This time let's have amplitude a in here, or actually r. No, a. Let's say this time instead of r, I will use the letter a with the purpose that this will be interpreted as amplitude of the simple harmonic motion. We want to break everything in the x direction. So let's think of this as a vector. So the position of this mass is this quantity. So that's your vector there. But let's break this into the x component. So that's your x. Okay. Let's project this down here. This is the same motion that I'm going to project it down there. This point brings it down here. The center point is here, and there is a negative point down there. This will be, as far as harmonic oscillation mode goes, x equal to 0. Notice this is circular motion. I'm connecting with simple harmonic motion. Simple harmonic motion is got by projecting this motion in the horizontal direction. That means if it's a vector, I have to take the x component. That means this distance. As far as x motion goes, that's that length, and let's say it is here. So if it is here, its x component is down there. As it moves along the circle, its x component decreases, and that projects it down there. And when it reaches right on the top, when angle is 90 degrees, it is at equilibrium. As it crosses that, it goes to the left, it reaches here, and then it starts going backward. So as this mass is going on a circle, its projection here is actually going along a line. This is going in a circular motion, but this is having an oscillatory motion. So this is circular motion. This is oscillatory. And there is a one-to-one connection there, in the sense that the oscillatory motion captures the x component of the position vector. So what is x here? So x is equal to, if that's a, we know how to project it in the x direction. It is cosine of the angle, but the angle is time dependent, right? Angle theta. So this is a times cosine of theta, but theta is omega t. So x is equal to a times cosine of omega t. That leads to some interpretations of what is a and what is omega. That's the only two quantities that is coming in. X is the how far you are from the equilibrium point. T is time, and two parameters, omega and a. A is, if of course it is the radius of the circle. When it is circular motion, we understand that, but when it comes to oscillatory motion, a is this point from x equal to 0. That's the maximum extent to which the mass is oscillating. That means if you were to stretch this to this point and leave it with velocity v equal to 0, that's the maximum stretch. So a is called the amplitude. So a here, so let me write here. So a is the amplitude of oscillation. What is omega? Down here, omega is related to how fast it is moving. It is uniformly rotating, but it tells you it is the angular speed. But angular speed in circular motion is related also to the time period. So this is equal to 2 pi over t, where t is the time period. So that gives us the interpretation that this is angular frequency, where t now is time period. It's the same idea. So angular frequency and time period are inverse of each other as far as, and if you put it in radians, there is a 2 pi that comes in. So it's time period. Same idea. So again, something going in a circle, but its projection is actually an oscillation. But this oscillation is not a trivial oscillation. It's not a normal motion, in the sense when x is equal to 0, so or when the particle is at x equal to 0, its velocity could be maximum, and as when it is right at that point, it could be coming to a rest. So this is not a uniform motion. In fact, it is having a cosine function associated with it. So let's plot that position time graph. So we have x as a function of time. We know that we have argued that x as a function of time is given by the cosine function. So, and we can also write this. It's instructive to write this as cosine of 2 pi over t, capital T times t. Seems to be there is more clutter there, but that way you exactly know what happens at t equal to capital T. At time t, when it is exactly the time period, they cancel each other, and that is cosine of 2 pi. Cosine of 2 pi is 1. So it again comes back. So there is a periodicity that comes out much more clearly when you write it as 2 pi over t times t. But this is sufficient, that has the same content in it. Let's say this is x-axis is time and y-axis is position. Right here, notice x was in the horizontal direction, so we are kind of twisting this whole thing. So that means to say that x can have a maximum and a minimum. So let's say that's a, so that's the amplitude, that's a maximum value x can take, and that's the minimum value x can take, so that's minus a. That's plus a, so that's plus a, and that's minus a. So the 2 points, that means to say now you should turn this, and this mass is actually oscillating like this. So in the x direction, it is plotting like that. But in the time, you can actually stretch it out. At t equal to 0, cosine of a cosine function is starts from 1. So that means it is plus a. And what happens at t equal to, let's say, time period divided by 4, that means to say you, so in the circular motion, you cannot see it in the plane there. So this is having a circular motion also, right? So let me put this here. There is a circular motion associated with this. That's your x equal to 0. So that's the projection there. That's the projection. As this moves in a circle, this actually goes in the vertical direction. So I've rotated the whole thing. So that leads to this motion to be in this form. So that's a cosine curve. And what is a time period? It starts repeating after 2 pi radians. That means to say capital T. So that's T. So that's the time period. That is the time it takes for this to start from here and come back in here. So it starts from here, goes to 0 there. So that's 0. So that's 1/4 of the circle. So that's T by 2. Sorry, T by 4. That's T by 2. By the time it has reached here, the mass is down here. That means the mass is down here. So that's minus a. It is at the extreme negative position. And then it climbs, as you complete the rest of the circle, it starts going in the upward direction. And this is 3t by 4 before the time period. And once you finish the whole circle, it reaches here, and then it keeps repeating again. So that's the oscillatory motion we are talking about. It is a simple harmonic motion in the sense that everything is very periodic, like whether you start from here or here or here, it's all the same. In that sense, it is a simple harmonic motion. Again, there are two parameters. One is the amplitude and one is the time period. Right? How often does this repeat? And what is the maximum stretch, right? When you are actually pulling it, how far do you stretch it? So that's the amplitude in this case. As far as the spring goes, it is called the amplitude by which the spring has been pulled. So that's good. So now we know what is the position time graph, but we would also like to know what about velocity? What about velocity of this mass as it is oscillating? It is clear that it comes to a stop at the extreme end there. This is x equal to 0 at the extreme end. It should come to a stop, and it will be fastest at x equal to 0. It pretty much zips by that x equal to 0, and then comes back to a rest there, and then keeps oscillating that way. So it should be exactly like position, but again, there is a periodicity in there. So what is a velocity? How can we decipher that? And once we know the velocity, what is acceleration? We would like to investigate those quantities. So let's go and go to the other board. So exactly like we could infer about the position using a circular motion, we can do the same thing for velocity also. Let's again have the same circular motion depicted here. So that's your position. And we said when we project it down there, that's your x equal to 0. And that's your x equal to, that's plus a, and that's minus a. And that is position. And we said that was x is equal to a cosine omega t. To get the velocity, we look at the component of velocity. So that's your velocity. If the position of the mass that is undergoing circular motion is this, and that's your angle theta, and there is another angle theta that's formed, that's here. What is that? So that's angle theta, that's velocity. V. So as far as the position goes, the angle theta it is making is with the horizontal, but when it comes to velocity, it is making an angle with the vertical. You can see that clearly by making this motion. As you make angle theta smaller and smaller, velocity should get vertical. Right? So that's how you can intuitively see that that angle has to be equal to theta. You can also use right triangle. You have to stretch this out. So that's angle theta. That's so that's 90 minus theta. So there is a direction that is perpendicular. So that's the same angle theta there. So either way, you can prove that. But once you know that's angle theta, then project it. Right? If we want to get the velocity, we project it along the x direction. So this component here would have an x component down there. That's your vertical and that's your horizontal. And if you notice, the horizontal component is opposite to the angle theta. So it is sine theta. So the velocity is equal to sine of the angle theta, which is omega t. Also, the velocity is in the second quadrant, right? If I were to show this clearly, so I'll erase that. So that's in the second quadrant. So that's in the second quadrant with angle theta here. So since it is in the second quadrant, x component will be negative. So that's negative sign for that. And what's its magnitude? This is circular motion. So that's omega r. That's omega times a. Omega times the radius, right? So that's acceleration. And this sine omega t. So how did I get these three pieces? That's your amplitude. Right? That's your magnitude. In circular motion, the magnitude of the velocity is given by angular velocity times the radius. That's angular velocity times the radius. And its x component is what is understood as the velocity in simple harmonic motion that has a sine component in it. So that's how sine comes in. Since it's in the second quadrant, there is a negative sign. So that's negative omega a sine omega t. So position, if it is a cosine omega t, velocity is minus omega a sine omega t. So let's see how that works. When it is right here, right exactly when it begins its motion, its velocity is 0. So it starts with velocity 0. At this point, velocity is equal to 0. As it goes inward, it is actually having the negative direction. So its velocity increases as it goes, so let's say at this point. And when it is moving to the left, and if it was right at the x equal to 0 point, its velocity is maximum. And then it starts slowing down again. So when it is down here, it slows down again, comes to a stop, and then starts increasing its motion again. So this is the opposite direction and comes to a stop again. And that should match with this. So let's plot sine of omega t and see if this matches whatever we are talking about. So if I were to plot velocity, so first of all, for reference, let me, is there more space? I think I can plot it here. So if this was my position, so that's t, and that's position plus a minus a, and that's time. And velocity in the same scale, so that's your time t, that's t by 2, that's t3, 3 times t by 2, and that's your quarter. So that's your t. And now this is sine function. So since velocity is given by the sine function, not only sine function, it is a negative sine function. Sine function would start with 0 and go up and then come down, but it's a negative of that. So remember, sine function is like this. So sine function would be like this, but it is negative of that. So I have to take the mirror image with respect to the time axis. So I'm plotting velocity here. So this would be like this. And starts, keeps going. So that's t by 2 and so on. Let's see if this matches at t equal to 0. It started down here on my left pointing finger. So that's velocity equal to 0. As it goes down, so when it reaches the center here, its velocity is a maximum, but to the negative direction. So that's the negative side here. So that's minus omega a. And on the top here, so that's plus omega a. So it reaches a maximum and then overshoots it and then starts decreasing again. And once it reaches 0, then again it goes in the positive direction and comes back. So it does clearly suggest that whenever the position is equal to 0, velocity is a maximum. Right? So here position was 0, velocity is maximum. At this point, velocity position is 0, velocity is maximum. So velocity is a maximum wherever position is 0. So that's a characteristic of simple harmonic motion. We would like to go further out in here and ask, what about acceleration? If we go back to this figure here, what is the acceleration? This is a circular motion. That's position. Velocity is tangential. Acceleration, remember, is in the radial direction. This is the centripetal acceleration, and it is not, it is exactly like position, but in the negative direction. So that's acceleration. And that clearly suggests that, oh, position is here, but acceleration is negative. That was our starting point, right? Acceleration has to be negative of x, and it can be scaled. So it is scaled with this angular frequency, but it is negative of x. That means this was your position, acceleration is negative, but this is in the vector form. If you take the component of this, this is along here, right? So it is now in the third quadrant. Accelerate position is in the first quadrant, velocity is in the second quadrant, acceleration is in the third quadrant. So when you take the component of that, that will give you negative again. So again, this is your acceleration. And if I were to write this down again, move this camera back. So acceleration now is, since it's in the third quadrant, it is negative, but still cosine. Right? It's cosine of omega t, because the angle is the angle is being represented with respect to the x-axis, and that's omega square a. Why is it omega square a? Because the centripetal acceleration is v square over r. Centripetal acceleration is v square over r, which is a, but velocity itself is omega times a square divided by a, which is omega square times a. We typically wrote it as omega square r. So that's your three results, that position has a cosine function, velocity has a negative sine function, and acceleration has negative of a cosine function, which is actually position itself. So this can also be thought of as minus omega square x, right? That's our starting point. So all this fits in. That's a verification that everything fits in. What about acceleration? How does it look like at x equal to 0? Right? Or wherever it is equilibrium point. So right at this point, acceleration is all vertical, no horizontal component, so that is no acceleration here, 0. When it is stretched maximum, so the acceleration is large, inward. When it is down here, acceleration is to the positive direction, very much like the force, and it is equal to 0 in here. And it is cosine function, but with a negative sign. That's what flips it. Remember that position is a maximum here, but it is exactly negative of that for acceleration. So if I were to plot this for acceleration also, it's time t, and again t, that's t by q. This is exactly like cosine, but flipped this time. So cosine goes to 0, and then a maximum at pi by 2. So this will go like this, and then comes back down there and repeats. What's the maximum value of acceleration? It starts from minus omega square a, and this is plus omega square. Those were the details, but let's summarize this and what are the points we need to keep in mind. We had to depend on geometry to get this motion because in general, this whole analysis comes out nicely if we use the understanding of calculus, but we have instead used geometry to derive our result. Okay, so summary is that position x is a cosine omega t, velocity for simple harmonic motion is v is equal to minus omega a sine omega t, and acceleration a is equal to minus omega square times a cosine omega t, which is also equal to minus omega square x, which is our defining feature. For any, whenever we see this equation, that acceleration of a quantity, it doesn't have to be x, it could be any other quantity. If the second change in a quantity depends on the quantity itself, then that will be our motion. So that's how we will interpret this. Let's do a simple example where these things shows up, just so that we know how to use this. Let's say we have a spring. So this is an example. Just to get used to how we evaluate this positions and velocity. Pretty straightforward, but it's since it is the first example, let's do a small catch up here. So let's say we are interested in the amplitude and the angular speed, but remember omega square was equal to k over m. So in the problem, we will be given that the spring constant k is equal, and let's choose a proper so that things cancel out. So we have 2 pi into 10 raised to 2, let's say, and it is Newton per meter. Force is equal to k times x, so the unit of spring constant is Newton per meter. And let us say that the mass is equal to 10 raised to 2, so that's 1.0 into 10 raised to 2 k. Oh, let's make it squared. So I should actually, yeah, so let's make this square, 4 pi square, so that when it comes out and divides it out, so that's actually 2 pi. So we immediately have omega square is equal to, those two cancel out, and I have 2 pi square, and that gives me omega is equal to 2 pi. That means the time period is omega was 2 pi over t. That means that the time period is equal to, so since omega is 2 pi, time period is 1.0, since two significant digits, so that's 1.0 seconds. So I chose the numbers appropriately so that it comes out in a nice manner. So the first step is from given the spring properties and the mass, we can get the time period and the omega or the angular frequency. The second thing that is to be given to us, so this is what is given to us, is the amplitude. Amplitude could be 10 centimeters, or let's say 1 meter. 1 meter. So that's what is, oh, I think that's out of the screen. So that's 1 meter. So let's say amplitude is 1 meter. So that's given to us. And then the question is, find the position. What is the position? Position at, let's say, 3 seconds. That's periodic. So let's say 1.25 seconds. And next could be velocity. What is acceleration? So on at 1.25 seconds, let's say. So we just have to put this in there. So x is equal to a times cosine omega t. Time period we said is 1 second. So that's, remember, this is equal to a times cosine of 2 pi over capital T times t. Put in the numbers here. So that's 1.0 meters times cosine of 2 pi over 1.0 times 1.25. So that's 5 over 4, and that gives us 5 pi over 2. 4 pi over 2 will be 2 pi, so it is basically pi by 2. So if you can put this in the calculator, make sure that you do this in radians. But this comes out to be 5 pi over 2. I can subtract out 4 pi out of it, and this will come out to be exactly 0. I did this in my head, but let's make sure that that comes out. Make sure you're in degrees. If you want, you can use 2 pi to be 360, right? That's another way if you want to work it out in degrees instead of radians. So that's cosine of 1.25 times 2 pi radians. And that's exactly 0. If that comes out to be 0. One could also calculate what is the velocity. So velocity, when it is right. So once we know that its position is actually 0, that means it's at the equilibrium point, so velocity has to be a maximum. So this is minus omega A times sine omega t, so that's equal to, so it should come out the maximum, just the omega times A itself. But let's do this. Omega we said was 2 pi, so that's minus 2 pi times 1.0 times sine of 2 pi over capital T, that's 1.0 times 1.25. But sine of 1.25 times 2 pi will come out to be exactly 1. So let's again do that. 1.25 times 2 pi. So that exactly comes out to be 1. So that's 2 pi. 2 times pi is 3.14 into 2, so 6.28. So that's 6.3. So it's minus 6.3 meters per second, right, to 2 significant digits. Acceleration similarly is minus omega squared A cosine omega t. But I don't have to redo this calculation because A times cosine omega t is x, which I know is 0. So that's minus omega squared times x. But x at this time, we have calculated this to be equal to 0. The acceleration will be equal to 0. Right? So that's how you would calculate how, given the time t and this parameter, first get the omega or the time period, either way, and plug in the numbers, and we can get all these three numbers. So that's simple harmonic motion. But there is one property that is very interesting in this, and that is obtained by actually doing conservation of energy principle in here. So let's investigate what happens to the energy in this scenario. So let's, we have position, velocity, and acceleration. So let's talk about energy. Energy, remember, so what's happening here is mass times acceleration, right? In the x direction is minus kx. That's only force associated with that. So the change in kinetic energy will be equal to the work done by the force, or by the spring force. We called it Ws. But since the spring force is a conservative force, this is the same as negative potential energy due to the spring. And potential energy due to the spring, we said, is half kx squared. That means that the change in potential energy plus the change in potential, so kinetic energy, will be equal to a constant. So let me write that again. Change in kinetic energy plus change in potential energy will be equal to 0. So since the change is 0, that means that the kinetic energy plus the potential energy will be equal to a constant. So if this is a constant, change in the left-hand side will be constant minus constant. So that will come out to be 0. So change will be 0. Change is 0 means that the quantity remains the same. What does that mean? What is kinetic energy? That's half mv squared. And what's the potential energy? That's half kx squared. And according to this energy conservation, these two should remain the same. So we calculated what the velocity of a particle or a mass moving, oscillating as a simple harmonic motion is. We know the position also, but apparently these two, if we were to square this should come out to be a constant all the time, at all time, at any time, at any time. By constant, it means that it doesn't change at all with respect to time. So this is supposed to stay the same. So let's, this we should be able to verify. So let's put this quantities in, right? So let's start from the left-hand side. This means left-hand side, right? That's the short for left-hand side. And let me substitute whatever we had for velocity. For velocity, we had minus omega A times sine omega t. And then square. And the potential energy has a square of position in it. So that's half k x squared. So that's A times sine omega t. Sorry, A times cosine omega t. Sorry. A times cosine omega t squared. And the claim is that this whole thing should come out to be a constant. So let's see how that works out. So that's equal to minus, since it is squared, so that does not contribute. The minus sign is done, so that is a half m omega square. Then there is the amplitude A, and that is sine square omega t plus half k, the spring constant k, and then again the amplitude square. Oh, this should be amplitude square. The first term I missed the square of the amplitude. Same thing for the potential energy. It's half Ka square times cosine square omega t. Whenever we did this spring examples earlier, we avoided this whole thing by talking about the extreme scenarios where either the spring was completely compressed or it was completely stretched out. Those were the situations we talked about. But here we now have a very general situation. We can do this at any time. And apparently it is still conserved. So it is constant. So how does this work out? It doesn't seem to have a common coefficient, but it is, in the sense, if you remember, omega square was actually k over m. So omega square, where can I write this? I think I can use the left hand. We had defined omega square as the ratio of k over m. In fact, omega in that sense is square root of k over m. Since it was a square of the quantity, so it's k over m. Omega square is k over m. That would cancel out one of the masses, and what we will have is half Ka square. Because k over m cancels out. That's sine square omega t plus half k squared. So how does this come out to be a constant? It doesn't seem to be, because there is time seen explicitly there, but there is an identity in trigonometry. One of the simplest identities is that sine square of an angle plus cosine square of an angle is always 1. Right? If I take the half k square, factor that out, what is left out is sine square plus cosine square, but that's exactly equal to 1. So it's half k square, which is indeed not dependent on time. K is the property of a spring. That doesn't change with time. And A is the amplitude, how much you stretched it out at the beginning, correct? So that doesn't change with time, because that depends only on the beginning quantity. So this is indeed constant. So the energy in the beginning is stored in the spring, and it can redistribute itself between the kinetic energy and potential energy, but it will always stay the same. So this is equal to half mv square at any time plus half kx square at any time. But that's constant, and now we know the value of the constant. That's half Ka square if you begin the motion by stretching things out. So now we know how to describe a simple harmonic motion, which is basically an oscillatory motion, and we also know how to analyze its energy. But now let's go out of this conceptual, or if we were to say a beachhead, right? We are now looking at this whole problem from the perspective of the spring. Can we go beyond that? So now let's rewrite this equation in a completely different manner. So erase this code. Oh, extra credit before I proceed. So let's say extra credit. So the extra credit is, notice when we say x is equal to a cosine omega t, the understanding is that at t equal to 0, these are called initial conditions. Initial conditions are that at t equal to 0, x is equal to a. At t equal to 0. And velocity v is equal to minus omega a sine omega t. And again, our initial conditions are velocity v is equal to 0, right? When you're releasing it, you start from rest. So at t equal to 0. But that need not be the only physical interpretation of an oscillation, right? For example, so this is, if you have this mass here, x equal to 0, and this is x equal to a, instead of stretching the spring and leaving it from here, I can actually push the mass m here. So give it a kick. So give it a kick with a velocity v in the beginning. That's another way of starting an oscillation. I don't have to stretch it and then release it. That's of course an easy way of generating oscillatory motion, but I can also kick it at x equal to 0. It will go to the maximum and then come back and then keep oscillating there. So there's another set of initial conditions. Another set of initial conditions. And that is that x is equal to 0 at t equal to 0. And velocity is equal to maximum, right? Velocity is equal to, let's say, v naught at t equal to 0. And pretty much the opposite of what we did here, right? Here, x was a maximum, v was 0 at time t equal to 0. We flipped it. X is now equal to 0, v is equal to maximum at time t equal to 0. And the question is, how will the solutions change, right? Clearly, this cannot satisfy this because at x equal to 0, at time t equal to 0, x should be equal to 0, and that doesn't satisfy. Cosine is a maximum at t equal to 0. So that's not satisfied. So you have to change this to get that. So think of this reversing this, right? So have that in mind and try to write down the solution for this initial condition. So the question is, what is x and what is v for this new initial conditions? With that, so let me finally point out, we want to generalize this. So conceptual leap is that, so we said we had the symbol, it's not really important, but we said second change in a quantity, or first let me write it for the x itself. So the second change in x is equal to minus omega squared times x. And that led to solutions. correct? X is equal to A cosine omega t. X is, so the solution is, if we encounter that property, and solution is X is equal to A cosine omega t. In general, a trigonometric function. But this could be any physical quantity. We don't have to talk about a spring. Anything that whose second change, this time I won't call it X, it's a quantity now. And we will work out the idea of a pendulum next time. And we will begin with this feature. Any physical quantity that changes in this manner. We will say we'll have a solution. We don't have to analyze this again and again. It will be the same feature that will show up. So this time we will say quantity. This could be anything. So I'm keeping this open. This could be like in a pendulum, this will be the angular, the angle beyond with which it oscillates. So pendulum is, remember this. So we will see that this angle actually has this oscillatory motion, but we don't have to reanalyze this. We just have to say the solution will be A times cosine omega t again. Exactly the same thing, except the difference will be in the interpretation, where A now is the amplitude in this quantity. So A, the dimension of A will be still, dimension of A will be equal to the dimension of the quantity that we are discussing. So that will be the conceptual leap we will make, and that will allow us to solve problems like the pendulum, which is not very trivial because its position does not go linearly or even quadratically as we have worked out or most of the problems we have worked on is related to linear or quadratic in time. And now we have a new kind of motion, which is the harmonic motion, relatively complicated structure in there, but we will be able to do the problem of pendulum in that manner. And I'll stop at this point. Good luck with your exam. I'll see you guys on Thursday.